This video will teach you how to set up a basic model using Autodesk Inventor with HSM Express installed, and talk about how to orient your model and ultimately generate the G code that you will use to machine your part in the Tormax CNC mill. First thing you have to do after you make your model, or preferably before you start making your model, is to make sure that it's oriented properly in terms of the X, Y, and Z plane. The three-axis mill has three axes of movement. The Z is the vertical axis where the drill bit or the end mill moves up and down. The X is the axis that goes left to right, which if you're standing in front of the machine has the longest distance of travel, somewhere around a foot. And then the Y is about 8 inches of travel. That's the one that moves front to back. So when you draw your part, if it's something rectangular or looking like this, you should draw it in the orientation that it'll be set up in the machine. So in this particular case here, the X is along the long axis, the Y is the short depth, and then the Z is the height here. So if you draw this, start with your initial extrusion in the XY plane to start. It'll simplify setting up this origin later on much easier, make it easier. The next thing you want to do after you finish your model is to make sure that the setup is correct. Here you want to make sure that your model box represents the size of the actual stock that you're going to be working from. This was likely a 2x4 that this was set up with, so this is set to 1.5 inches high, the length and width, and so on and so forth. Next thing you want to notice that the origin is actually origin with a corner. This is important because the first step when you use the CNC mill is that you have to orient the end mill or the machine itself with where the piece is clamped in the machine. So if this is your 000, then what you would do is use a combination of gauges and mills or in the CNC machine to actually reference this corner of this workpiece as the 000. If this is set incorrectly, then your axis will be off backwards, your Z height could be reversed, and you could end up with problems with your piece not being cut properly, or in worst case, you can end up breaking the machine or crashing the end mill into the vise, which could cause damage to one or both of those. So make sure this is set up correctly, preferably with the Z in the vertical direction, the X moving left to right, and the Y front to back like you see here. Then we're going to talk about cutting operations. So there's a variety of operations from facing, the pocket, and so on that you should have learned about through the different HSM Express tutorials. In this one here, we're going to talk about the pocket, which is probably the most common. I'm going to mention a few things that you should be aware of. So here, 4 operations were set up to make this part here. In this particular one here, first, this is the 2D pocket that this person used. So let's expand that and take a look at what's in here. Once this is set here, you can see first off the tool that was chosen is tool number 2. This is a 1/2 inch flat 2-flute end mill. First thing you want to notice is that I set up a library on the Google Drive, which you should download and install to your system. That's a topic of another video, because you want to make sure that the tools that you're selecting from that tool library match the actual tool library that you have on the machine. Not just the size and dimensions of the bit, but the actual number. Notice this is tool number 2, so when you go to actually machine your part, if the machine prompts you to enter tool number 2, it'll be much easier if you grab the tool that's actually labeled number 2 versus another one that you have to figure out the differences in dimensions for. Next thing here, we'll notice the feeds and speeds. This is important specifically even more important as we get into harder materials such as aluminum and metals for milling. There's 3 main variables that you need to pay attention to here. The spindle speed and the cutting feed rate are the 2 things that you're going to set, along with the plunge feed rate down here. So the plunge feed rate controls how fast the bit actually plunges or drills into the material. The spindle speed is how fast the spindle is spinning. For most things, we set that to 5,000 RPMs. For aluminum and any kind of plastics we're working with, is generally max speed. If we start doing anything with steel or ferrous metals, then we'll probably have to slow that down. But in order to get the feed rate figured out, there's a online calculator which I linked in Google Classroom called FSW Wizard. I'm going to talk about how to use this for a second. So if you click on the link from the announcement on November 23rd, you can find that link to this page here. So First thing we do on this page is we want to set up the material we're working with. So this thing doesn't have a huge library of materials. So if we're working with like PVC or wood or something like that, we'll scroll onto the plastics, and I'm using this pattern modeling board. This is probably the least dense material we have here. Mahogany is a type of wood. You can probably use either one of those. If you're working with aluminum or something or another metal, you would pick it from the list. Next thing you want to do is pick what kind of end mill we're using. Most of them are solid end mills. We have the material for most of ours is HSS, which stands for high-speed steel with no coating. We're working in inches, almost everything. Then this asks for the diameter of the tool bits. This is a 1/2-inch diameter tool bit. It says two flutes on it, which means there's 2 cutting edges. Most common types are 2 and 4. We have both, so make sure you use the correct one. Length is self-explanatory, flute length and all this kind of stuff. These things you really don't need to worry about as much. What is important here is the DOC and WOC. DOC is the depth of cut, WOC is the width of cut. So width of cut means if you're doing a slotting operation, which basically means you're cutting a slot in a material, the entire bit is engaged, meaning the entire diameter of the bit, the entire radial width. So in that case, if you check the slot pocket, this defaults to the full width, which means that this number here matches this number here. DOC is the depth of cut. That's how deep we're going in each plunge. A general rule of thumb is you don't want to plunge any deeper than the radius of the tool bit. So for example, this is a 1/2-inch diameter cutter. Half of that would be the radius, which is a 1/4 inch. You don't want to plunge any deeper than that. Depending on the material you're working with, the larger the bit is, the more resilient it'll be to breaking. So you might be able to increase that a little bit. But again, it depends on the hardness of the material and the type of cut you're doing. The next thing we need to change is the max RPM. The max RPM of the Tormac is 5,100 RPMs. We're going to set it just to 5,000. That's a simple number to remember. So once I've set all this up here, I can hit the calculate button. Then this outputs a couple numbers here that are important. Notice the RPM is still 5,000. That's what we entered. But the second thing that's calculated here is the feed rate in inches per minute. This is calculated at 56.70. So we can round that to somewhere around 55. If we want to go a little less, that's always less is a little bit better. It's a little bit more conservative and less chance of doing any damage. So I'll call this 55 inches per minute. From this 55 inches per minute, the surface speed is derived. That has to do with the speed that the outer circumference of the bit is moving with respect to the workpiece. Don't get too carried away with what that means, but just know that the RPM and the feed rate is what we're actually going to enter into HSM Express for that particular operation. So if I go back to my model here, in here I make sure I type in 5,000 RPMs for my spindle speed, and I come down to cutting feed rate, which is the 4th box down, and here I have 50, in this case 56 inches per minute. You want to make sure that the units agree too. If this is 56 feet per minute, that's a big difference. So you want to make sure that it's in actual inches per minute. The second thing is the plunge feed rate. I don't have an established table for these, so you want to generally make sure this is low, somewhere around 10 to 15 inches per minute is probably fine for most soft materials. The second thing is the lead in feed rate and the lead out feed rate. What these have to do with is the rate of speed that when the bit engages or disengages from a cut. So in other words, when it starts cutting and or finishes cutting. Generally, you want that to be slower than your actual cutting feed rate. So here this is set at 40. Our feed rate is at 55. If you're unsure, you can always drop these down. Generally, the smaller the bit, the lower these should be. So if this was an 1/8-inch diameter cutter, I would probably drop this down to even 10 or 15. These are not going to have a big impact on your machining time. The biggest impact will be this cutting feed rate and also your depth of cut, which I'll talk about next. So then we'll hit OK once we've got these feeds and speeds set correctly. Then you'll see updates here. The next thing I want to talk about is depth of cut. This is important too because a couple things. This significantly affects your machining time. It also affects the loads on the machine. So I've opened up the same operation here. Now I've clicked on this tab here that says passes. There's 2 things here that you should be aware of. There's the passes section here,